For question number 3A in the free response section, it says a company designs a spinning toy by using the family of functions cx root 4 minus x squared, where c is a positive constant. So it gives us this curve here, and depending on c, it's going to give us different kind of height of that curve. Each spinning toy is shaped as solid generated by a solid being revolved around the x-axis. So the solid's going to be revolved around the x-axis like that. So part A says find the area of the region in the first quadrant bounded by the x-axis in the graph of cx. Cx root 4 minus x squared for c equals 6. Okay, so first things first, we need to find the zeros. Okay, so we need to figure out where is the zero of these functions here and here. And we find the zeros by setting the equation equal to 0, and we can solve this. In general, regardless of what c is, this will still have the same zeros as this function here, and we can see that we have a 0 at x equals 0, and solving this part of the equation, we get x equals plus minus square root 4, which is plus minus 2. Okay, so we can solve this equation. We know that this is x is 2, x is 0, and if we graph the negative side of this, we can have the negative 2 root there. So that's the first thing. We need to make sure we find the bounds that we're going to integrate. So we want to find the area. So we want to find the area under this curve using the integral of that curve. And the integral is going to look like this. So the area is equal to the integral from 0 to 2 of the function. We're going to replace the c with a 6. So 6x root 4 minus x squared dx. This involves a substitution to be able to integrate this. So we're going to use our substitution as the inside function is going to be u. So we're going to let u equal 4 minus x squared. And then my du, the du portion of this, du is equal to negative 2x dx. Okay, and then I'm going to, since I have my x dx here, I can just algebraically rearrange this to du over 2 is x dx. So I'm going to replace the x dx with a du divided by negative 2. So when I do this, I just have to remember that when I change my variable of integration, I need to make sure that I indicate that on my bounds. So my bounds are going to be x equals 0 to 2. I'm going to take that 6 outside because it's a constant. And I'm also going to take that divide by negative 2 on the outside as well. Okay, because that's also a constant. And then I replace the rest of this. I have my square root of u. And then I have my my divide by 2, so all I need to then include in here is my du. Okay, so my du over 2 goes together as replacing the x dx. So this represents then my integral. I can integrate this. Okay, so I'm going to undifferentiate or anti-differentiate that, so I end up with negative 3. This becomes u to the power. I'm going to increase the power by 1, and I'm going to divide by that power, and my bounds are going to be at x equals 0 to x equals 2. Okay, simplifying this expression, I get a is equal to, this becomes negative 2, u to the 3 over 2. I'm going to replace the u. I'm going to back substitute for the u. So I'm just going to replace the u with my 4 minus x squared. And then I can change my bounds of integration back to x's, so then I can just write it as 0 to 2. Okay, and then plugging this in, the area under that curve is going to be negative 2. This is going to be 4 minus 2 squared, okay, which is 0 minus 4 minus 0 squared. It's going to be 0, so it's going to be 4 to the power 3 over 2. And working this out, a is equal to negative 2. This is going to be negative square root 4 is 2, cubed is 8. So I get an area that's equal to positive 16 units squared. In this case, the units are inches, so the area is going to be 16 inches squared.